Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
All right, let's take a look at lesson 7.2.3. This is called slope in a different representation. Okay, so once again, we kind of went over this, but this is giving us a little bit more detail on how to look at graphs and determine the slope or growth rate of each line, because we're going to have to do that when we're trying to find the rule that goes with the line of best fit for our scatter plots. So first thing I want to do is I want to front load this concept, and I think I might have brought this up in homework or yesterday's lesson, the idea of what lattice points are. And so lattice points are points on the coordinate grid where the grid lines intersect. So you see your coordinate grids are made up of these horizontal and vertical lines. This right here would be considered a lattice point because it's where the vertical and the horizontal intersect each other. There's a lattice point, there's a lattice point, there's a lattice point. But this is not a lattice point because it's in the middle of no man's land. This would not be a lattice point because it's only on one vertical line, but there's no horizontal line that goes through that. So we always want the lattice points to be the intersection of these grids, and this is one of the reasons why we always want to do our graphing on coordinate grid paper so we can identify these lattice points. And the coordinates of lattice points are always going to be integers. We don't want to find any of the in-between points because we just don't. You're guessing at the value of where this would be. It looks like it's 1/2, but it could be 0.49. So we don't want to mess with that. And I suppose you wouldn't have to have lattice points. Let me actually show you this right here. If you were scaling your axes when you're counting by halves instead of counting by ones, then I suppose you could have a halfway point be considered a lattice point because it would still be an intersection. So, take a look at this guy right there. That's a lattice point. That's a lattice point. And that trend should continue. If you go down 1, 2, 3 units and then 4 to the right to get there, you should be able to go down another 3 and another 4 to the right to get to the next lattice point. And then if you go up in reverse, instead of going down 3, go up 3, and then go 4 to the left instead of to the right, and you should see other lattice points appearing. Okay, so in lesson 7.2.2, you learned about how to use a number to describe the steepness of a line. Today, you will work with different representations of lines and look for how the slope can be found in each representation. As you work with your study team, keep the following questions in mind. And of course, you're not working with study teams right now, so as you're working through this, think about these kinds of questions. What is being compared to find my slope ratio, and what would it look like in another representation? All right, so a planting manual printed the graphs below so that the gardeners could predict the height of trees after planting. Jill wants to figure out the rate that each tree will grow. She remembers that the slope is a ratio of the vertical change to the horizontal change between any 2 points on a line. So remember, slope is what I call rise over run, but more often I refer to it as the change in y, the vertical change, over the change in x, which would be the horizontal change. The units for the vertical change are the same as the y-axis, and the units of the horizontal change are the same as the x-axis. Finding the slope for each graph will allow her to compare the change in height to the change in time. Okay, so this resource page, 7.2.3's resource page, can be printed off of my Google Classroom if you choose to use it, or you could just reproduce it in your journals. You could do that too. Okay, so on this resource page, draw and label a slope triangle on the line in graph 1. Then write the slope ratio. How fast does the tree in graph 1 grow? All right, so here is graph number 1. So I am going to look for those lattice points, right? And it looks like you got one here. Looks like there's one here. Looks like there's one here and here. Well, there's a lot of them. Did I skip one? Yeah, I skipped one there. So if I started here and I went up, I would go up 2 and 1 to the right. Or I could start here and go up 4 and go 2 to the right. So it appears as if the slope ratio, m, is going to be 2 over 1 or equal to 2. So that's what I'm going to declare right here. And that would be, we would refer to that, since looking at this, this is the height is 2 meters, and this is the number of years. So it'd be 2 meters in 1 year. And I think, yeah, because that's the slope of the line. There we go. All right, can you find the slope on graph 2 just by looking at the line? Why or why not? When it is difficult to read the slope on a graph, look for points where the line appears to pass through lattice points, right? Lattice point here, lattice point there. And use those points to create a slope triangle. There's the right triangle where you got your rise over your run, or your vertical change over your horizontal change. And then find the slope for graph 2. Okay, so here we go. Let's take, I'll do that color. It looks like the vertical change is 2 and the horizontal change appears to be 3. So we would say the slope for this line is going to be, wait, is that right? Is that the right one? I don't know if this is the right one. Hold on for a second. I was thinking they were talking about this guy right there, but they're actually talking about this guy right here. So let's check this again. Looks like here is one lattice point. Here's another. Here's another. There's another. And there's another. So in every one of these situations, oh, it goes up 3 and goes 2 to the right. So the slope ratio in this situation is 3 over 2. Got it. I mistakenly thought they were talking about this one, not the one on the resource page. So the slope is 3 over 2, which is the same as 1.5. So that literally means that this tree is growing 1.5 meters every year, or 3 meters every 2 years. So on the resource page, now let's use lattice points to draw the slope triangles and find the slopes for graphs 3 and 4. Okay, why don't you go ahead and pause, since I did 1 and 2 for you. Why don't you go ahead and replicate that and see if you can come up with the slope ratios for this graph here, graph 3, and this graph here, graph 4. Go ahead and pause and then unpause when you're ready for the reveal. All right, let's take a look and see what we've got here. I'll do that. It looks like this is a proportional type situation, and looking for lattice points. Does that look like one right there? This goes up 2, 3 to the right, so the next one should be up 2, 3 to the right. Yep, that looks like a lattice point. Up 2, 3 to the right, up 2, 3 to the right. So our change in y is 2, and our change in x is 3, so the slope ratio has to be 2/3. And in this one, it's going to start here at 4 and go here. Up 2, 3 to the right. So up 2, yep, that's it. Up 2, 3 to the right, up 2, 3 to the right. So these two lines appear to be parallel to each other, having the exact same slope ratio. All right, so it says 3 different students look at the line graphed here at the right, and each drew a different slope triangle. Their slope triangles are labeled A. Oh, there's A, here's B, and here is C. Now, your task is to find the length of the horizontal and vertical sides of each of these slope triangles. And sometimes I call them growth triangles. What is the relationship between triangles A, B, and C? Explain your answer and use what you learned in chapter 6 about ratios of side lengths of similar figures to help you if you feel like you need that. Okay, go ahead and take some time. Do the counting here. This is on your resource page. So go ahead and mark on that resource page if you copied it off on your printer, or if you want to draw this in, make sure that you get those points in the right locations and see if you can determine what each of the slope ratios are for each one of those growth or slope triangles. Okay, so I go over to triangle A, and it looks like the change in y is 5, the change in x is 4. When I go to triangle B, the change in y is 15, the change in x is 12. And when I go to triangle C, the change in y is 10, the change in x is 8. All of those ratios, 5 over 4, 15 over 12, 8, 10 over 8, those are all equivalent ratios to each other. So that means that all of the slope triangles are similar triangles, right? What is the relationship between the triangles? They all have corresponding side lengths, right? So if you double the side length of this, it becomes 8. You double this, it becomes 10. When you triple this, it becomes 12. When you triple that, it becomes 15. So those are all similar triangles. So when you find the slope ratios of each one of them, A is 5/4, B is 15/12, and C is 10/8. And it says the numbers in the slope ratios found by the students are all different. Does this mean that the slope of the line changes depending on which points you pick? And the answer is no, it doesn't. All the ratios are equivalent to each other. When you simplify each one of them, they simplify down to 5/4. And if you convert all of them to their decimal form, it would end up being 1.25. So another student said her slope triangle goes up 20 units for every 16 units it goes to the right. Where could her slope triangle be? Draw a possible slope triangle for her. All right, so I will do this right here. So I'm going to start at the y-intercept, and I'm going to color this guy orange. How's that for a nice color? No, let's do this color of orange. All right, so right there, and if she said it goes up 20 for every 16 it goes to the right, I'm going to start by going up 20. So that's 2, which means I have to go up to 22. And then it needs to go 16 to the right. So it's going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is that 16 right there? Yep, that's 16 right there. So what I'll probably do is this. Let me go the other direction. Let me take this, color it that, do it like this and that, and I would go, this guy would come out to here to 16, and this guy would go up to there, it should be 20. Simplify each of the 4. Okay, we've already talked about this. All of them simplified down to 5/4 or 1.25. That is the slope ratio. So what is the lesson to be learned here? Look at all these different lattice points that we get in this. Let me do this in purple now. No, I'll do it in yellow. That's a nice color of yellow. All of these, 1, 2, 3, 4, 1, 2, 3, 4, 5. Well, hold on for a second. Hold on for a second. All of these lattice points, all of them, it doesn't matter which ones you choose. I probably shouldn't have chosen that. That's a little bit off, but whatever. It doesn't matter which 2 sets of lattice points you use. Your ratio of your rise over your run or your change in y over the change in x can always be simplified down. So if you chose these as your lattice points, you just simplify it down to that slope ratio. So you can pick any 2 lattice points that you want on your line to figure out what the slope of the line is. Okay. Did you know that a bank will pay you money called interest when you place your money in a savings account? The amount you receive is a portion of the amount you deposit. The interest rate often varies with each bank. And we're going to get deep into interest, simple and compound interest in Chapter 8. But right now, let's just see how simple interest ends up showing up on a graph. Thomas and Ryan have each invested the same amount of money in different bank accounts that earn simple interest. Simple interest means that the same amount of interest is added for each time period. It's always based on the amount that you deposit into an account, not on your new balance as you move forward. So it always ends up being the same because whatever you put in the first time, that's always going to be the amount that you deposited in the account. So your interest is always based on that every time it gets added onto your total. So in this case, the interest is added each week, right? So time in weeks is shown as our x-axis, and the amount of interest earned is our y-axis. Thomas and Ryan decided to compare their rate of earnings by graphing how much interest each of them has earned over time. The graphs are shown below. Okay, so there's a table that goes along with these graphs. And so the first thing I would notice is this. If I were to decide who was making more money, the first thing I would look at would be to look at the graphs, right? And Ryan's appears to be steeper than Thomas's, right? So at first glance, it sure looks like Ryan is making more money in interest than Thomas. But then you look at the table, and it's like, okay, his unit rate is 60 cents per week. What does his unit rate end up being? Is that the same? Is it more? What is that? How do they compare? So now that we've looked at the graphs, it says when you look at the graph, which investment seems to be growing the fastest? And as I just said, it sure looks like Ryan's is because it appears steeper. Now, these are the tables that we were talking about. Which table reflects Tom's interest and which one reflects Ryan's interest, and how do you know? Well, coming back and looking over here, it says in 1 week, Tom earned 60 cents. So this one looks like it matches up with Tom. And in 2 weeks, he earned $1. And so this one looks like it's matching up with Ryan. In fact, there's the 6 weeks making $3 entry right there. So we're going to say that the table on the left belongs to Thomas and the table on the right belongs to Ryan. And because we just matched up the data points with points on the graphs. So use the tables to find the interest earned in dollars to time in weeks for each of them. Whose money is growing faster? Well, we know this one, Thomas, is making 60 cents per week. How much is Ryan making per week? And if you took $1 divided by 2 to get the unit rate, you would be correct. That would be 50 cents per week for Ryan. So does our answer here for C match up with what we had predicted based on the lines? And the answer is no, it doesn't. We thought that Ryan's graph being steeper meant that he made more money. But here's the thing. If you're going to compare the steepness of two graphs, they both have to reference the exact same number lines for the X and the Y axis. Let's come back and look at those. Do you see how far apart each one of these units is spaced in the X axis for Thomas's graph? Do you see how they're not spaced as far for Ryan? That affects the appearance of the graph and the appearance of the steepness. If you were to graph both of these on this graph, in fact, let's just do that right now. Let me see if I can figure this out. Or should I do this one over here? No, I'll do this one on this one. All right, so 1 week was about 60 cents, which is going to be somewhere around here. 10 was $6, right? Do we even have it 10 weeks and $6? I don't. Oh no, I don't know if I'm going to be able to do this. Let's try this. 4 and 240. So 240 is going to be somewhere around here. Let me use a little tool here to help me with this. I'm going to take 4 and go up like this, and I'm going to take 240, which is right around there, and put it here. And so that one is going to be right there. Okay, so let's get rid of you, get rid of you, and now let's take this graph, which I will color it in red, and they're all proportional in nature, so let's start at 0, 0. Stop it. Okay, now you can see if they are both graphed on the exact same line, Thomas's is indeed steeper than Ryan's. So Thomas makes more per week in interest. His 60 cents is greater than Ryan's 50 cents per week. All right, the students in a study team are now arguing about who has graphed the steepest line. Assume that they're all set up on the same axes with the same scale, okay? Here's some information. Lucy's slope ratio, when she finds her last points and figures out the rise over the run or the change in Y over the change in X, is 7 over 5. 3 is 5 over 7. F is 4 over 10. And theta is 12 over 10. So you can use these slopes of their lines to visualize how each of the lines would look on the graph. Can you, just looking at those slope ratios, determine which one would be the steepest? Okay, so let's say explain completely who has the steepest line and who has the least steep line. So we don't care about the ones in the middle. Which one is steepest? Which one is the least steep? Go ahead and see if you can figure that out, and unpause when you're ready to move on. All right, so what we should probably do is we should take each one of these and we should get them either into decimal form or get them so that they all have the exact same denominator. If we change them so they all have the same denominator, I think our denominator would need to be 70. So we multiply this times 7, and that would end up being 98 over 70. This times 7, no, this times 14 would be 70. You know what? I don't want to do it that way. I'm changing my mind. Let's change them all to decimal equivalents because I can use my calculator for that one. 7 divided by 5 is equal to 1.4. So this is going to be the same as 1.4. 14 over 10 is also equal to 1.4. 5 over 7, what does that end up being? That's going to be a repeating decimal. 5 divided by 7 is equal to 0.714, rounded off. And 12 over 10, that's 1.2. Okay, so which one appears to be the steepest? Looks like Lucy and Cliff are both the steepest at 1.4, and Breeze is the least steep. This is the only one that's less than 1, is 5/7 or 7.14. All right, last problem. Which lines on the graph at the right and on your resource page, this is the last graph that's on the resource page if you printed it off, appear to have the same slope? Which lines are the steepest? First make a prediction, then check your prediction by finding the slope of each line in the graph. Okay, so looking at them, can you tell which ones appear to be the steeper ones and which ones are less steep? It looks like A and C are parallel to each other, doesn't it? And they are steeper than B and D, which also appear to be parallel. So I'm going to go ahead and say that lines A and C are the same slope and B and D are the same slope, and A and C are the steepest. So I would like for you, for our last activity, is find the slopes of lines A and C to verify that they are indeed parallel to each other, and find the slopes of B and D to verify that they are parallel to each other. Then we should be able to compare those slope ratios to prove that A's and C's is greater than B's and D's. Okay? Last problem, take your time on this, find some lattice points, look at, create your growth triangles, and then figure out the slopes. All right, what do I notice about A and C? Both of them, when you look at lattice points, show that when the vertical change is 3 units and the horizontal change is 2 units, so both of those end up having a slope ratio of 3/2. And then when you look at the blue growth triangles, you can see this one has a vertical change of 4 units and a horizontal change of 5. This is the same, 1, 2, 3, 4, 1, 2, 3, 4, 5. So both of those have a slight slope ratio of 4/5. And A and C have slope ratios that are greater than 1. This is 1.5. And this is 1.5, and B and D have one less than 1. This is 0.8 and 0.8 if you put them in the decimal form. So absolutely, the slope ratios for A and C are greater than the slope ratios for B and D. All right, so that concludes our lesson for today. Let's move on to our next activity. Take care. Bye. Bye.
Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.